So if Jakob is ready, and I see him, he is ready, then I can announce the next speaker is Jakob Tougaard, and he's from Aarhus University, Aarhus, Denmark, and you're going to address the GES tools. Jakob, the floor is yours.
Thank you very much, and thank you very much for the opportunity to present our contribution to the JOMOPANS project. It's been a very exciting project, and we've been very happy to be part of it. And our main share of this, we have maintained monitoring stations on behalf of the Danish Environmental Protection Agency and supplied the data to the project. But our main contribution is in development of the GES tool and the developing the models or the tools to evaluate the underwater noise and the impact on the marine ecosystems. And of course, we have not done this alone. Many of the other partners in JOMOPANS have played a central role in doing this. So the ideas behind this is very much common shared ideas of the entire project group. Okay. Let's see. Yeah. So what is good environmental status when it comes to underwater noise? So a lot of it relates back to the Marine Strategy Framework Directive, and there the expression is rather vague, that it's underwater noise should not be at levels that adversely affect the marine environment. But what does that mean? And so in order to we have to be more specific in order to get closer to evaluating whether we have GES in the North Sea or not. So one place we can look could be in a HELCOM document where there was a workshop on exactly this issue some years ago, and there the conclusion was that in order to have GES with respect to noise, then there were two components. One is that noise levels should not affect the energy budgets of the animals in a degree that affects the population of animals. So that is something that relates to disturbing the animals, displacing the animals from habitat and so on. And the other point is that the noise should not be at levels that induce masking, which is interference with communication. And that should also not be at a level where it has an influence on the population size, on the ability of animals to find mates and nurse their youngs and so on. So there are at least these two components to GES. So if we take disturbance first, then this is something that has been discussed a lot over the last 20 years when it comes to marine mammals. And there are some, to many people, well-known figures here, the so-called PCAT model and the PCOT model, that gives the framework for how to address this, how individual sounds lead to behavioral changes in the animals, and that has some consequences for the time budgets and the energetic status of animals and so on and so forth, and that has long-term consequences for survival and reproduction in these species, and thereby it has population effects. So in principle, these things are well known. In that sense, there are no missing pieces. But to get actual numbers on these interactions has turned out to be very difficult. And there's a lot of work remaining to be done before these frameworks are really operational, before we can come from the maps that Chris showed to some interference about actual effects at the population level. And it's slightly different when we come to. Sorry. Another issue with behavioral disturbance and displacement is that what we can call the habitat quality paradox. That there is more to habitat quality than just noise, and if it's a good habitat, if there's a lot of food or a lot of potential partners or shelter for predators or whatever, animals will habituate to the noise because there are other advantages to be there, and we know that this from ourselves very well, that in the hotel lobby it's very quiet out there, but there are no people. It's not interesting. But in the bar, even though it's very, very noisy, that's where the drinks are, that's where the food is, and that's where there's possibilities to socialize and maybe even mate. So that should be kept in mind when analyzing this, because this means that habituation is central, and also the context of the habitat and the other circumstances have influences on the way the noise affects the animals. So this makes it complicated to analyze this. Masking is in many ways more straightforward because it's more closely related to physics, because we have an effect of noise in the surroundings increasing. That means that it becomes more difficult to communicate. But then animals and as well as ourselves, we have compensatory measures. We can do something. We can put a hand behind our ear. We can start shouting and so on. And that will improve the signal to noise ratio and mean that we can continue to communicate. But at some point, we run out of these, or animals run out of these compensatory measures. The signal to noise, the noise in the surroundings becomes so high that there is no other way to improve signal to noise ratio than to move closer. So that's the last resort. And that means that in the end, the effect of masking is a loss in communication space. So it's a habitat loss. You can easily view it as a way of habitat loss. It's temporary, of course, because the same moment the noise is gone, then communication is restored. It's also very important to keep in mind that masking is a natural phenomenon, because the noise can be any kind of noise, not just man-made noise, but weather and other animals, and especially other animals of your own species. So I live here very close to a large colony of rooks, and they are noisy, especially in the afternoon. And but imagine being two rooks in this colony trying to communicate with each other, with all the other birds trying to communicate at the same time. So masking is something that animals experience on a regular basis, and they have ways to handle it. Same goes for marine mammals and fish, although we know less about the mechanics about it, but the ambient noise in the sea fluctuates a lot, and so the animals are accustomed to this. So masking in itself is not the problem. The problem is when there's too much masking too often. And so that is what we want to quantify. We want to quantify when there is extra masking caused by our own activities, in this case ships. And so because we're dealing with physics here, it's the masking is very closely linked to the signal to noise ratio, then it's not possible for the animals to habituate, because it's something that happens outside of their control. They can't influence the signal to noise ratio in other ways than moving closer to each other. So how do we address this in the JOMOPANS? What have we done to work with this? Well, the models can, or the way the noise is modeled is that we have the natural sources, which is wind and waves. So that's the reference state. So that is a model scenario for what the noise would be if there were no human activities in the North Sea. So that's a good starting point. And then we can add ships, and in that case we get what we call here the current state. So that's the model's estimate of what the actual, in this case, median noise conditions are in the 125 hertz band in the North Sea in month of June, I think. So how does this relate to masking? Well, we can say that if the current condition exceeds the reference state by some lower limit of concern, then we can say the communication is limited by the ship noise. And so far we have used two different values, 6 dB and 20 dB, as limits for concern. This is closely linked to what we have defined as the excess, which is simply the difference between the current state and the reference state. So we can say that masking is a problem when excess exceeds this lower limit of concern, either 6 dB or 20 dB, depending on which map we're looking at. So excess here is modeled on a very short time scale. It's modeled on a 1 second time scale, as Chris was explaining. And the reason for this is that masking is almost instantaneous. So masking only occurs in the time when the noise is there. As soon as the noise is gone, the masking is gone. So it's not very helpful to model masking based on long-term averages, because that doesn't say much about the actual conditions the animals are experiencing. But for an overall assessment of GES, we need to make the assessment over a longer period, either 1 month or 1 year. So that's why we introduced the measure dominance here. So that's the percent of the time of the evaluation window, 1 month or 1 year, where the excess is above our lower limit of concern. So that is what you see on the map to the right. With the dark areas, that's where the dominance is high, and the white areas are where it's low. So there you can see that the central part of the North Sea, for example, the dominance is very low in this 125 hertz band. Most of the time, noise in this band is determined by natural sources. Whereas not surprisingly, in the English Channel and along the coast of Netherlands, but also the coast of Jutland, the dominance is very high, and most of the time the noise is, the communication is limited by ship noise. So this does not in itself say something about the impact on the animals. It only says that if there are animals in these areas that are trying to communicate in this frequency band, then they will be limited by ship noise. Whether that's a genuine problem for the animals or not, that is further down the line to study that. But in this sense, we are looking, as Chris was saying, also on the pressure on the environment here. And we have the map, and that can be used to study this spatial distribution of the ship noise. But we can also make, or we can evaluate it in 2 dimensions, time and area, at the same time by means of the pressure function, which is the curve to the upper right here, and that's based on the distribution of dominance over the total area. So that's the histogram to the right, where you can see in this case in the North Sea, a large part of the North Sea has low levels of dominance, and 50% of the area has a dominance that is 22% or lower. And then there are some areas, 10% of the area, that has a high dominance above 66%. So that's a way you can use this pressure function to analyze the overall conditions in the North Sea. You can of course do exactly the same for sub-regions of the North Sea, which is what is done here on the next slide. So here the North Sea, or the JOMOPANS area, has been divided into 6 sub-regions, and curves have been made for each of these 6 areas, and you can see the curves to the upper right. And you can see that there are 2 groups of 3 areas, 3 with high noise load, and 3 others with the lower noise load. And if we want to express this in an even simpler way, just by a single digit, we can use the area below the curve as a simple index. And the rationale behind this is that if the dominance increases in certain parts of the North Sea, this means that the index will increase, the area will increase. And if the affected area increases, it also means that the area below the curve will increase. So in that sense, there is a direct connection between the conditions in the North Sea and this index. There are lots of details that needs to be sorted out, but that's the general logic behind this. And so we have the histograms. The histogram in the lower right shows this index for these 6 different areas. I will not go into further details on what this, how we can interpret this with respect to the animals, but this is as far as we are now. And there's also the next step, which I will skip today, is how we can add the animals, but because we can do that if we know something about where the animals are and whether there are certain areas where they are more sensitive to noise than others, we can perform a weighting of this curve and factor this knowledge into the equations. Right now, we're simply assuming that the animals are evenly distributed everywhere and they are equally sensitive everywhere. But I invite you to explore some of this even further by the online GES tool, and Emily, I think, should be ready to give you a quick guided tour of this tool. So thank you very much.
Can everyone hear me? Yeah. All right. Oh, this is going to be a little bit weird because the camera's over here, but let's see if I can just do something like this. All right, that's fine. So this is the GES tool. Let me pull it up. So as Chris was talking before, and Niels, I mean, we have about 1,200 maps. I'm not going to show you all of the maps because that seems like not a great use of our time, but I will pull up all of the maps just for January. As you can see, there is roughly 100 of them. So these are all of the types of maps that were generated for the JOMOPANS project. I saw in the questions that you guys have a lot of interest about like why we chose 20 dB and 6 dB, but we have the 20 dB and 6 dB as well as the different hertz, the total, the 3rd octave level bands in this tool, along with different sound dominance like the median wind and then the instantaneous wind that Jakob was talking about. But here, let's pull up the excess of the instantaneous wind at 125 third octave level. So there it is. So this is different than the dominance map, but you can see, zoom right in here. It gives the same basic information. So in this map, white is going to be your louder, where the louder sources are, or dark colors like Dodger Bank. Right there, that's where it's a little bit more quiet. And you can clearly see some shipping lanes pop out like we did in the other map that Jakob was showing. We have it going around Denmark here into the Skagerrak, as well as the English Channel, of course. And if we flip right back into looking at the sound dominance at 20 dB, select layer, and that looks more like the map that Jakob was just showing you. So you can see the utility here. You can view, in theory, all of the maps that we've provided. Right now we have only a couple of months uploaded, but they are all the maps that Chris has provided to the tool. But the cool thing is also we have this calculator. So Jakob brought up briefly that we can look at different animals or different regions within the GES tool. So right away, I'm going to pull up the same map that we were just looking at, which is sound dominance, instantaneous wind, 20 dB. There it is. So we have a couple of different choices here, but I'm going to go with the 125. Select the layer, and it's right there. And then we have two options here as well, which is species habitat and area region. So as provided by the group in Norway, I'm going to pull up the cod spawning map that a lot of you guys seem to be pretty keen on before. So this is an annual map, area map. So in these this tool, you can use either an area mask, like so that would be all of the areas that we think cod are spawning in, or a species density, which there are some species maps like the harbor porpoise that exist within the North Sea. But for right now, let's just focus on cod spawning. There we go. Let's find the layer. Great, select that. And then let's just look at Denmark. All of the cod spawning areas, in Denmark. Okay, find layer. So here you have, select. All right, so we have our three maps. We have our dominance map over here. We have our cod spawning map right in the middle, and then all the way to the right is just the area of Danish waters. And so we can run the calculator, and it gives us information about all three of the layers that we included in this calculation. It has the dominance histogram that Jakob went through before, the CD function, and of course your pressure curve as well with this pressure index. So that's the tool. It's pretty straightforward and easy to use. It allows you to explore a lot more than I can really give a demo for, but let's move it back. Yeah, I guess, does anybody have any questions about that or about Jakob's talk as well?
Okay, thank you very much for that explanation, Emily. And yes, are there any questions about this? About Jakob's presentation or about the tool?
Yeah, there were many questions. Also many answers on the chat. Thanks to that also for Chris and others. One question maybe that has not been answered yet. Are you able to translate the lower limit of concern noise level into a percentage of reduction in effective hearing?
Yes, you can. To some degree, under some simplifying assumptions, you can say that if the noise increases with 6 dB, then you have a reduction in communication range of 50%. And if you have an increase of 20 dB, that corresponds roughly to a reduction of communication distance by 90%.
Thanks, Jakob. Another question? Could it be possible to determine the excess level from the measured data and compare with the model? How should the reference state be defined in case of measured data?
Yeah, that's a good question. I don't have a straight answer to that, but I know that there are people working on this question. So you can get from the measured data, you can get ambient noise by filtering out only the quietest periods in a day, and assume that that's the periods where you have no closed ships. But there is no way you can filter away the distant ships, because you can't separate the distant ships from each other and from the natural ambient noise. But you can get close, so you can get something that will approximate the excess level from measurements, I think.
Any more questions?
Yes, maybe I can also comment on that we have a lot of data, and we can certainly extend on the statistical analysis of those data, and what are the different percentiles and how they, if whether, for instance, the 10 percentile, which is only exceeded in 10% in 90% of the time, so that's a very low level. Whether that corresponds more or less to background sound, then you can explore whether you can derive that from the measurement data only. But that's as we have seen that the North Sea is there's always noise on the North Sea. Shipping noise is always dominating most of the other sounds.
Cool. Thanks, Niels. There are also many compliments that I would like to bring over for the GS tool. So people look forward to collaborate.
We have a lot to thank Michael
you.
Carter for that. He did a really great job bringing what we wanted to see to life. So, and I think he's in the chat today.
I think we probably need to stress here that it's all for pressure sensitive species, isn't it? Because it's just pressure related modeling. And as soon as we talk about particle motion, then we get a different story.
Yes, that's exactly true. And so that goes for a lot of fish and invertebrates as well. But that's an entirely different story. And I think we are as far behind as anyone else on this issue. I know that Chris is planning to do something in the Saturn project, but within JOMOPANS, we've concentrated on pressure.
Yeah, and it's just important to realize that with directionality being important for particle motion, then the masking is likely to be much less than what we envision with the pressure relationship between signal and noise. But maybe deterrence actually can be potentially more, can be longer, because sound is audible in a background noise for longer. So it can work both ways, but different for masking and disturbance.
Yes.
Okay, are there any more? Jakob, did you want to add something, or?
Yeah. So masking, when it comes to particle motion, I don't even know what to envision there. What that is like. I don't think anyone has looked at that at all.
Now, theoretically, you can imagine that because directionality plays a role, it's not just the overall level that probably the first modeling will be about. That doesn't add too much, I think, on top of the pressure analysis, because we need to know the directionality. And a boat with a source from a particular direction, while the background is omnidirectional wave noise, and then the boat is better audible because of the spatial unmasking. And processes like that are widespread and likely, occurring on all animals that are sensitive to the directionality through particle motion. But there's a long way to go, I guess, before we get a GES tool in that sense. But something to look forward to. if you ask me. Okay, I think we should move on, and we see you back later in the session after